All right, thank you very much. And first of all, thank you very much to the organizers for putting together this great lecture series and for inviting me here to speak. Okay, so as we are probably all aware, right, when we go and implement an algorithm on a computer, we have to use some finite number of bits to store and compute with. Okay, all of our real numbers, right? And so the way the standard that everyone uses is floating point arithmetic. And so there are a number of different forms of floating point arithmetic, some more common than others. So if you just open up MATLAB and start typing, you're going to be using double precision as a default. Okay, so this is the IEEE double type or FP64. So the 64 is the number of bits that we have. Right, so all floating point numbers we can put in this format. So we have a sign bit, some number of exponent bits, and some number of fraction bits. Right, and so how we distribute the bits among those different parts is going to determine properties like what range of numbers we can represent and how precise our computations are. All right, so like I said, this is kind of the default that people use is double precision. Okay, you can also use single precision in MATLAB, and that's been common in GPUs for a long time. More recently, we've seen commercial hardware emerge that has even lower precisions. Okay, so there's the IEEE half precision format or FP16. All right, so here we have 5 bits for the exponent, 10 for the fraction. There's also a non-IEEE compliant format called bfloat16, also 16 bits, but this distributes them a little differently. The idea being we have closer to the range of single precision in representable numbers, and the sacrifice for that is a slightly lower round off. Okay, so here I have a little table that summarizes this. So here I have the size in bits, the range of representable numbers, and this U is my unit round off. Okay, so meaning whenever I store a number in this format, I make some rounding error. Whenever I do a computation, I make some rounding error that's bounded by these quantities. Okay. All right, and so like I said, single precision, double precision, these have been around for a long time. More and more recently, we're seeing hardware commercially available that has 16-bit and even lower precisions. And this is largely driven by machine learning applications. Okay, so people want to train neural networks. You don't need much precision to do that. So they use, very few bits to do that. Okay, so all of this development of this hardware has kind of been motivated by machine learning. All right, so half precision or the FP16 format was first defined as a storage format in 2008 in the IEEE standard. And since then, we've seen, here's just a kind of a list of hardware that's emerged that has these capabilities. Okay, so some notable ones are these NVIDIA GPUs. Okay, and so a major innovation with the V100 that came out in 2017 were these tensor cores, so what's called tensor core instructions. And so what these are doing is they enable you to do a 4x4 matrix multiply in a single clock cycle, right? And so that means that half precision is not just 4x faster, it's 16x faster, right, than just using double. So this in double precision you would get 7 teraflops performance. If you use half precision plus these tensor cores, you can get theoretically up to 112 teraflops performance just on one GPU. Okay. And so since then, NVIDIA, there's also things like Google's TPU, Intel AI chips. The most recent thing that was just announced a couple months ago, this is NVIDIA's H100, right, which is now one thing to point out here is that they now have quarter precision, right, so FP8, right, and so they actually use something that's, or they're going to have something that's like dynamic, that depending on what you're doing, some more bits will be allocated to the exponent versus fraction, right? And it's really expected that as we go, to higher and higher performance computers, as we push towards exascale, that these computers will, start having extensive support for reduced precision arithmetic, maybe even potentially lower than 8-bit. Okay, so this is stuff that's commercially available now, right? And so how can we use this in numerical linear algebra? All right, so like I said, this is stuff that was invented for machine learning, but we have this hardware, it's available, it's in our computers, it's in our supercomputers. What else can we use this for? Right, so here is a plot from a 2018 paper that's showing performance in various precisions of just doing LU factorization. So this is just LU with partial pivoting. All right, so I have teraflops per second performance on the y-axis. and different matrix sizes here. And I'll talk more about this later. This is just kind of giving you a preview. All right, so this orange line here, so this is doing double precision. So calling this this LAPACK function in double precision. All right, purple is single precision. All right, the blue is half precision. And then this teal is the half precision, also making use of these tensor cores on this NVIDIA V100 GPU. All right, and so you can see that, we can, these speedups are not necessarily just theoretical. We can also, get very good performance speedups for linear algebra computations, traditional linear algebra computations. All right, so it's worth seeing, what we can use this hardware for. All right, and so this is some data from the top 500 list. And so the top 500 list is a ranking of the top 500 supercomputers in the world that comes out twice a year. And I'll talk about more about how that ranking is done soon. All right, so here's just a sample from the most recent list in November 2021. And so here I've just taken these accelerator families that feature half precision, and I'm just looking at how many of the top 500 machines in the world have low precision capabilities, have these half precision and lower capabilities. Okay, and so if we look at the total system share, it's about 27%. So 1 in 4 of the top supercomputers in the world has these capabilities. Right, and if you compare that number to just a couple years ago, you can see that this number is growing. Okay, so I would say this is kind of, from my perspective anyway, the biggest architectural change that we've seen in the top 500 list is the inclusion of these accelerators that have low precision capability. All right, so back to what this top 500 list is. Okay, so like I said, exascale, we're pushing towards exascale computing. When are we going to declare that we've achieved victory? Okay, and so the metric, for better or for worse, for success is performance on the HPL LinPack benchmark. Okay, so high performance LinPack. And what this benchmark is doing is it's solving dense linear system, AX equals B, using Gaussian elimination with partial pivoting and double precision. All right, this is traditionally the way that we have ranked supercomputers, and some might argue that that's a good thing. Some might argue that's a bad thing. Okay, so we will declare we have reached exascale computing when a supercomputer achieves exascale performance on this benchmark. Okay, so that's 10 to the 18 floating point operations per second. All right, but a lot of people have known for a long time, okay, this HPL benchmark is compute bound. This is doing BLAS3 stuff. This is not necessarily a good indication at all of how my application, my real application, might perform if I go to run it on this computer. Okay, so very rarely do we have something that's nicely compute bound and all BLAS3. All right, so in practice, we have sparse matrices, and we know those are harder to optimize and implement on hardware. We have graph computations, et cetera. Okay, and so people have come up with a number of alternative benchmarks that are complementary to the HPL benchmark. Things like the Graph 500, things like HPCG, which is doing conjugate gradient, and things like the Green 500, which is looking at energy usage instead of just performance. Okay, so it's kind of in recent years, people have come up with other benchmarks, which are now really seen as complementary to HPL. Okay, so one major thing to notice is that HPL doesn't tell me anything about mixed precision, right? The mixed precision capabilities of these machines. Okay, it's doing everything in double precision. It doesn't tell me how well these machines could do on this same problem if they were to be allowed to use lower precision. Right, and it turns out, so if we are willing to count lower than double precision flops as flops, the computers we have today are already exascale machines, right? And so this is the first instance I know of a machine reaching exaflop performance. This is an article from 2018. So this was from Oak Ridge National Lab, where they used mixed precision in a genomics code. Okay. All right, so this motivates a new benchmark, right? And so this new benchmark is called HPL AI, all right? It's not actually doing any AI. It's the AI is named because we're using the hardware that was kind of developed for AI. All right, so what does this benchmark actually do? It's doing the same thing as HPL. okay? It's still solving a dense linear system, AX equals B. It's still giving me results to double precision accuracy. But to do it, it's using a mixed precision iterative refinement approach, okay? And so the nice thing about this approach is that this can be implemented in a way that's takes advantage of this mixed precision hardware. And so later in the talk, I will come back and tell you more about the algorithms that are behind this benchmark. All right, so here are just the most recent results from November 2021 on the HPLI benchmark, okay? And so there's more and more machines that are running this. The number of machines that are, people that are participating grows every year. And so just some things to notice is that the top two machines are exceeding exaflop performance on this, okay? On the same problem that the HPL benchmark is solving, right? So this Fugaku machine is doing 2 exaflops. And another thing to notice is over here in this column, we have the speed up over HPL. Okay, so again, still solving AX equals B, all right? Still solving it to double precision accuracy, but we can do it much faster, okay, if we use mixed precision. Okay. So here's just a slide that is showing you all the different uses of mixed precision within numerical linear algebra that currently exist. You can find all of these in a survey paper published last year in IJHBC. Okay, and so some of these go back to Wilkinson doing iterative refinement in the 60s. Some of them are more recent. All right, so we have specialized BLAs now that people are developing, that exploit these tensor core instructions that are now available. There's like I said, historical work in iterative refinement. There's work on doing mixed precision matrix factorizations, solving eigenvalue problems, both dense and sparse, and sparse direct solvers, orthogonalization, multigrid, and Krylov subspace methods. Okay, and some of these papers have rigorous theoretical error analysis behind them, right? What is the goal when we're designing a mixed precision numerical linear algebra algorithm, right? There's 2 goals. First, we want to use mixed precision or low precision in a way such that my code is faster. Okay, that's the goal. I want to improve performance. Right. The second is that I don't want to use mixed precision or low precision in a way such that I destroy my numerical stability or destroy the accuracy that I get. Okay. And so, it would ideally like to have, at least a guarantee on the second part. And so some of these results, you do have these guarantees. You say, if these conditions are met, I can do this in low precision and still get, this accuracy. Right. Some of these are more experimental. Just people said, okay, we tried them, we did a high performance implementation, and things still work for our particular applications. Okay. And so from my perspective, it's very important actually that we have these theoretical guarantees, right? It's very important that we have some error analysis underlying the use of low and mixed precision. Okay. And I think that's important for 2 reasons. First, by actually doing the error analysis, I might notice places where I could use low precision that I didn't notice before. And second, on many applications, you want some guarantee. Okay, I want guarantee that my solver will still be stable, that my answer will still be right in some sense. All right, and so in this next part of the talk, I'm going to first, again, try and convince you of why this is important and what can go wrong. Right, if we just kind of blindly use low precision in places without thinking too much about it. Okay, and so there are a number of challenges we have to think about. So the first, okay, if I use low precision in this part of my code, do the existing error bounds still apply? Okay, we have very nice error bounds that say, okay, this algorithm is backwards stable. If this condition is met, I'm guaranteed this accuracy that's related to the machine precision, et cetera. All right, and if you see a lot of these error bounds in the literature, okay, they'll have, I need, n times u is less than 1 or something like that. So n is some dimensional constant, u again is the unit round off, right? So if it, usually if this quantity exceeds 1, there's not much you can say, right? So most error bounds assume that that's true. Okay, but so what's happening in the exascale era? So okay, n is getting bigger and u is I'm using lower and lower precision. So these are kind of conflicting, right? All right, so the first is, do error bounds still apply? I might have to think more about my dimensional constants now. Okay, so if I'm using half precision, this u is around 10 to the minus 4. Okay, and that means problems with n greater than 10 to the 4, I can't say anything about. I can't say the algorithm's numerically stable. I can't say that this is going to work. Okay, and so that's a very small problem in the context of high performance computing. All right, so one solution that people have come up with to this is taking a probabilistic approach to reduce these dimensional constants in error bounds. Right, and so this goes back, I think, to Wilkinson, who in this rule of thumb that I can take this n and replace it with the square root of n everywhere. Right, and so this has been a kind of rule of thumb for a long time. More recently, Nick Hyam and others have rigorously shown this. You can have a probabilistic approach that shows you can take square root of n, or maybe even less than square root of n if your data has mean zero and some nice properties like that. Okay, so that might only get you so far. The second thing to worry about is now we have a smaller range of representable numbers. Okay, so my matrix might have values that are very big and very small in it. Okay, so if I go, even if I just store my matrix in a lower precision, all right, I'm going to get some nans, some imps, some overflow. All right, just storing my matrix. All right, and so if things that are very close to zero now become zeros, I can lose important properties, right? I can lose, for example, positive definiteness. If I lose positive definiteness, I can't use the conjugate gradient method anymore, et cetera. Okay, so these are things that we have to pay attention to. And so one solution to that is before I go and store my matrix in a lower precision, I can do some sophisticated shifting and scaling algorithms. Okay, and so one example of this is in this article by Nick Hyam and Srikara Pranesh, which talk about squeezing a matrix into half precision. And here the scaling factors and the quantities that you choose in your algorithm are somewhat related to the pivot growth factor, or anticipated pivot growth factor in LU factorization. So you might have a different scaling algorithm depending on what algorithm you're doing. Okay, again, this will help you, but can only take you so far. And then, of course, we have a larger unit round off. Okay, so I'll lose something small when I'm just storing my matrix, not even doing any computation, just storing my matrix in a lower precision, I lose something. And then every computation I do, every floating point operation I do, I lose a little more. Okay, and so these things can accumulate and they can also be amplified, right? So it's important to understand that. Okay, so then we ask, does any of this matter? Does it matter, and when does it matter? Okay, and for a long time, people in a lot of areas have said it doesn't matter. When we were just talking about using double precision. So when we do scientific computing or data analysis, we have so many sources of inexactness. We don't just have floating point roundup error. Okay, so we have imperfect data, right? We have measurement errors. We have modeling errors, discretization errors, if we're talking about the world of PDEs. And on top of that, we often use some intentional approximation at the algorithm level to make things faster. Okay, so I might do some model order reduction. I might do low rank or hierarchical approximation of my matrix to make computation faster. Or I might sparsify, I might randomly drop very small entries. I might use a randomized algorithm. Okay, so we have a whole hierarchy of errors that we make and are kind of okay with a lot of the time on top of that. Yeah.
There is a optimization error. You can never go
yes. Yes, perfect. Yes, a whole hierarchy of errors. And worrying about all of these together is a problem that I don't think a lot of people do. We try to abstract a lot of this away. And usually it's the floating point roundoff error that gets abstracted away because that's very small, right? A double precision, 10 to the minus 16, that's, people usually say, okay, I can kind of ignore that. I'm making much greater errors, when I'm just, doing these kind of higher level algorithmic approximations. And so in a lot of papers on these topics, you'll see that floating point roundoff error is totally ignored. Okay, so and that's fine a lot of the time. I mean, that's valid a lot of the time. Okay, but it might not be valid anymore as we go to lower and lower precisions. Okay, so if I go half, quarter, etc., you might start to see floating point roundoff error matter where it didn't matter before. Okay, and so let me just show you some examples of this. And so the first is in randomized algorithms. So this is the algorithm for the randomized SVD. Okay, so I have a tall skinny matrix A. I want to compute a truncated SVD with some parameter K. Okay. All right, so the way to do that in a randomized way is I take some 2K or some oversampling factor omega here. And so this is a matrix whose entries are sampled from a standard normal distribution or a subsampled random Fourier transform or something like this. Okay, so I do A times this random matrix. I get a Y, and then I do a QR of this. And so this kind of first step here is called the randomized rangefinder problem. Really, all I want from this is the Q, right? So I want a Q whose columns are in some sense capturing the essence of A. Okay, so once I have this Q, all right, then I can do Q transpose A. I get this tiny matrix B, and then I'll compute the SVD of this tiny matrix B. Okay, and so that will give me the singular values and right singular vectors, and then I can recover the left singular vectors, again, using this Q. All right, so this is how you do the randomized SVD. And in the literature, the bounds that are given, if you look at papers like Halko, Martinson, and Trop and things like that, they give error bounds of this form. They say, okay, if this first part produces a Q that satisfies this, right, this is less than some epsilon, then the resulting error in your SVD will be also bounded by this epsilon. Okay, so those are the bounds that are approved. All right, and so the question is, do those hold in finite precision? All right, so let me just look at some examples. So I'm just going to use MATLAB RAND SVD matrices. Right, so here I'm generating a matrix of dimension 100 by 40 with condition number 10 to the 6th, and I'm going to change this mode. This mode is controlling the singular value distribution. Okay, and K here, I'm going to do a rank 15 approximation. All right, so I have 4 different quantities I want to show you. The first, all right, so this without any diacritical marks or subscripts. This is the non-randomized SVD, so deterministic, built-in MATLAB SVD using exact arithmetic, simulated exact arithmetic. Okay, these with hats, I'm doing the randomized SVD, also in simulated exact arithmetic. And then here, these last 2, I'm doing the randomized SVD, but subscript D for double and subscript H for half. Okay, so here I'll generate these using mode 3 random matrices, which gives me geometrically distributed singular values. And you can see that all these errors are the same. Okay, so finite precision doesn't really play a role. I don't notice it. Okay, even if I use half precision, I don't notice it. All right, so now if I use mode 1, where I have one large singular value, the rest small. Okay, so here I get 10 to the minus 6, right? When the non-randomized exact SVD. All right, using the randomized one, I lose something versus the deterministic case, with just a little bit. I don't notice double precision at all, okay? But I do lose about an order of magnitude going to half, right? Versus the randomized, the exact precision randomized. All right, so I lose an order of magnitude. So I do start to eventually notice the round off error, right? Depending on my problem. And second, and maybe the most important to me, is that, okay, the bound no longer holds, okay? So remember, my bound was if this quantity is less than whatever, then this is also less than that whatever. Okay, so now my bound no longer holds. And this is even just for just a small problem. Okay, and so this stuff does start to matter. So it's important to analyze these things in finite precision, not only so I know when this happens, but so when I know when I can safely do this. Okay, yeah. Okay, this is no, to the working precision. Yeah, to half precision. Yes. Yeah, to half precision. Yeah. Okay, another example is in hierarchical and low rank approximations. Okay, and so here's just an example of block low rank approximation. So I have some matrix A. I'm going to approximate in this format. So I'll keep the diagonal blocks. The off diagonal blocks I'm going to represent by some low rank pieces. Right, there's a lot of work by Nick Hyam and Theo Mary and others on mixed and low precision and block low rank matrix computations. Okay, so here's just my example. I have an inverse multi-quadratic kernel, right? So a non-compact radial basis function. All right, and so here I'm picking 16 random points in R2, right? And I'm gonna create this matrix according to this definition. All right, and then I'm going to approximate it by a 2 by 2 block low rank guy, A tilde. All right, so this matrix A is symmetric positive definite, so it's desirable that my approximation should also be symmetric positive definite. Okay. All right, so if I do this using exact arithmetic, so to compress or to get these low rank approximations of the off diagonal blocks, I'm going to use the SVD. And so if I do that whole computation in exact arithmetic, okay, here's what I get. And so the eigenvalues of the original A are these blue X's. The eigenvalues of my approximation are red circles. Okay, and here's what I get if I do that SVD computation for these off diagonal blocks in half precision. Okay, and now let's zoom in. All right, and so what do we notice? We notice we've lost something important here. We've lost positive definiteness. Right, so now I have an eigenvalue that is less than 0 here. And I will stress that this can happen even in exact arithmetic. Okay, but now it can happen not only in exact arithmetic, it can also happen because of using low precision. Okay, so it's important to understand when this happens, right? So if I was going to use this, for example, as a preconditioner in the conjugate gradient method, it might not work so well anymore. Okay, I've lost my positive definiteness. Okay, and my third example is in something that's my favorite topic, iterative methods for solving linear systems. All right, and so here I am just plotting the relative error in the A norm versus the iteration for the conjugate gradient method in double, single, and half precisions. Okay, and here my matrix, I'm just going to use diagonal matrices. Here my matrix is just a diagonal matrix with equally spaced eigenvalues between 10 to the minus 3 and 1. Okay, so this is not particularly ill conditioned, right? And so here's what I see. All right, so the convergence is not affected here by the use of low precision. Okay, low precision only changes the attainable accuracy that I get. It only changes the where I level off. Okay, and this will level off at some point because of deviation of this true and updated residual. Okay, so this might lead me to believe, okay, I can, if I only need 10 to the minus 2, I can always run CG in, half precision, no problem. Okay, but this is a very particular problem. This is a matrix with equally spaced eigenvalues. What if I look at something different? Okay, so here I have a matrix that has, please note, the same condition number. Okay, the same smallest eigenvalue and largest eigenvalue. Okay, but now my eigenvalues are distributed differently. So they accumulate towards the low end of the spectrum, which means I have large outlying eigenvalues. Okay, and I think this is not very well known maybe, but the case where you have large outlying eigenvalues is the case where CG is extra affected by round off error, okay, especially in terms of convergence. All right, and so now we see for this problem, again, this is still just a diagonal problem. Now I lose not only attainable accuracy, but my convergence rate is worse, okay, which means that if half precision or single precision, whatever, is faster, well, if I'm solving to a particular accuracy, it might not be as fast as I would want it to be. Okay, so I might kind of undo any performance benefits I get from using low precision, since I'm going to take more iterations to converge. Okay, so this is something that is important to consider. Okay, so the takeaways from this first part of the talk is that first, low precision can have massive performance benefits. Okay, not just theoretically, not just for machine learning, but in numerical linear algebra as well. Right, but it's very important that we use these capabilities with caution. Okay, and it's important to really, in order to fully first, understand the limitations, but to also understand the opportunities, we need to understand the theoretical basis and have some analysis of these algorithms in mixed precision arithmetic. Okay, so in the next part of the talk, I will talk about some of my own work of myself at Nick Hyam and that others have built on in what we can do when what we can achieve when we actually go and do the analysis. All right, and so this I'm talking about iterative refinements or for solving a linear system AX equals B. And again, this is not something of course we came up with. This goes back to Wilkinson and Moeller, and a lot of people have worked on this over the years. So there are a number of different variants, flavors of iterative refinement that you get depending on how you do these precisions. So first, just the overview. First, I'm going to get some initial approximate solution x naught. Right? I'm going to solve for my initial approximate solution. That's typically done using LU factorization. And then I'm going to iterate until I'm satisfied. I'm not going to talk about convergence criteria here. Okay, so I'll compute my residual. All right, I will solve for the error. All right, so setting the residual equal as my right-hand side and solving for this correction term. And then I will update my approximate solution. Okay, and so how do I do this solve? Well, if I keep these LU factors around, I can just do the solve very easily. Okay, and so one variant of this that has was gained popularity, introduced by Dagara and many other people is, what if I do this low part, this LU factorization here, the n cubed part of the computation in low precision? Okay, and so that's kind of the motivation there. So they said already, I think they were using single precision at the time, but they said, okay, I can use low precision in this expensive part and get performance benefits.
Can I ask a quick question about that? So you talk about computing the LU factorization in half, but then in the solve AAI or RI, you say precision U. So
yeah, yes, it should be effectively, you don't really gain anything by doing it in higher than half there. Yeah. But I think that this is kind of just the framework that they set up where I have, low precision and then one for everything else. Yeah. But if you use a solver besides LU factorization, it might make a difference. But if you're just using the low precision LU factors, you might as well do that in half precision. Okay, and so what do the error bounds here say? All right, so if I do this low precision variant, all right, so I can say that as long as the infinity norm condition number of my matrix A is less than 1 over the square root of my unit round off, all right, then my relative forward error is bounded in terms of the unit round off and this condition number of A and X. And then the relative norm-wise and component-wise backward errors are both on the order of the unit round-off. Okay, and so there are other variants of this besides this low precision factorization. Okay, so there's also what's called traditional iterative refinement due to Wilkinson, which goes back to Wilkinson that says, okay, do everything in precision U except the computation of the residual. Okay, do the residual computation in extra precision. Okay, and if you do that, this version, this what I'll call traditional iterative refinement, you get rid of this conned term in the forward error. Okay, there's also, you can do fixed precision iterative refinement, right? So people worked on that a lot in the 70s and 80s, where I just use 1 precision for everything, right? So here, then your condition becomes just U, and you still have this term in the forward error. Okay, and so all these existing error analyses kind of assume that I had 2 precisions, right? I have a U and then a something else, either U squared or U half, all right? And that made sense. That made a lot of sense when we had, at most double and single precision in our hardware. Okay, but today we have a whole list of different precisions, and so maybe it makes sense to combine, these ideas of Wilkinson and this low precision factorization and use 3 precisions. Okay. And so this is the idea, right? So now I'm going to have 3 different precisions. I'll have the precision with which I'm doing the factorization, this U sub F, right? I'll have my working precision, the default U, and then I'll have this U sub R, which is the residual precision. Okay, and so we can fit, these existing types, these historical types of iterative refinement into this framework. All right, so traditional iterative refinement. So I'm doing everything in the working precision except the extra precision in the residual computation. Right, I'm doing fixed precision, everything's the same, or then this low precision factorization, okay, where this is UF is the square root of U. Okay, so now I can do things like half single double, half single quad, half, double, quad. And so I'll always kind of refer to these triplets in this order: the factorization precision, the working precision, and the residual precision. And I will try and be consistent with this coloring scheme. Okay, so some key, just to point out some key parts of the analysis. So the first is we can obtain tighter upper bounds. Okay, and so how do we do that? So one thing to notice if you look at almost any error analysis is that bounds of this form are used, right? Right. So I'm bounding the norm of A times a vector by the norm of A times the norm of that vector. Okay, very typical thing to do. All right, but it turns out that this can be this is a very bad upper bound depending on where we are in the iteration. Okay, so what I will do instead is I'm going to define a quantity mu sub I. That's the exact ratio between the left and right hand sides here, and I'm going to reason about its value. Okay. All right, so if I think, okay, I'm at the beginning of my iterative refinement. All right, so I've already done the initial LU solve, right? I expect my backward error to already be small, but my forward error to still be pretty large. Okay, and so what that translates to is I expect this mu is very small, right, close to its lower bound of 1 over the condition number at the beginning. Okay, this mu will only get close to 1, meaning that this only gets close to equality once I've almost converged. So close to convergence, I expect that my my residual and my forward error are both small, and that means that mu goes closer and closer to 1. Okay. All right, and so reasoning about that way, we can actually obtain tighter bounds than previous people did. Okay, the second, and this will be clear in a few slides later, why we want to do this. We want to allow for a general solver. Okay, so and well, of course, we're not the first ones to do this, but I will introduce this new use of S to be the effective precision of the solve. All right, so this is not a real hardware precision. In cases of interest, it's either going to take on the values of U sub F or U. Okay, and I'm going to make 3 assumptions on my solver. Okay, the solver could be anything. Okay, first, I'm going to assume that the normalized relative forward error is bounded by some multiple of this U sub S and is less than 1. Okay, and so just let's look at an example what these bounds are for the example of just doing an LU solve. Okay, so here's standard, textbook normalized relative forward error here. Okay, the second, I'm going to assume something on on the normalized relative backward error. Okay, that's bounded by some maximum of these 2 quantities times this U sub S. Okay, and again, here's what that looks like for standard LU solve. And then I'm going to assume that the component-wise relative backward error is bounded by some multiple of U sub S. Right, and so again, here's what that looks like for the standard LU solve. Okay, so what does that mean? That means, okay, in the case of just using an LU solve, the effective solve precision is the precision in which I have computed the LU factors, okay, which makes sense. Okay, and so looking at let me just state the results. Okay, so again, I have my 3 precisions, right? And so what is the forward error result? Okay, so if I do this iterative refinement in these 3 different precisions, and I have an effective solver precision U sub S, as long as this quantity phi is less than 1, which only depends on the effective precision of the solve, then I know that my forward error will get smaller and smaller by this factor until I reach the limiting forward error. Okay, and the limiting forward error depends on the precision in which I compute the residual and the working precision. Okay, and so notice also that this mu shows up here, right? So this condition number, this infinity norm condition number only comes into play once I'm very close to convergence. Right? Usually it'll be this smaller, potentially smaller quantity. Okay, and so the analogous, kind of traditional bounds is this, right? So I just have the infinity norm condition number in there. I don't get this slightly better bound. Okay, and here is the backward error result. Okay, so if I do iterative refinement in these 3 precisions, I can say, right, again, as long as this quantity phi, right, is less than 1, then my backward error will get smaller and smaller until I reach this limiting level. All right, so again, this here now, in contrast to the forward error, this just depends on the working precision. And again, this quantity phi, which again is dictating whether or not I'm converging, is dependent on the effective precision of the solve. Okay, and so let me just kind of that's might be hard to parse. Let me just summarize that in a table. Okay, so I'm assuming that I'm using standard LU-based iterative refinement, right? Which again, as a reminder, means that the effective solve precision is the factorization precision. And so I have here's different scenarios of what I'm using for the factorization, what I'm using for the working precision, and what I'm using for the residual, right? So H is half, S is single, D is double, and Q is quad. Okay, in this column, I have the maximum infinity norm condition number for which the rest of the results are guaranteed, right? So if the condition number of A is less than this, then I'm guaranteed this in norm-wise and component-wise backward error, and this in forward error. Okay, and so a lot of the existing flavors of iterative refinement fall into this category. So here's the low precision factorization versions. Okay, this row represents the fixed precision. And then I have a traditional, okay, where the residual computation is done in double the working precision. Okay, and these ones that are left are my new 3 precision variants. Okay, and so some things to point out. If I compare these 3 precision versions to the low precision factorization, so by using a 3rd precision for the residual computation, I get rid of the condition number terms in the forward error. Okay, so that's nice. Okay, if I compare to traditional iterative refinement, basically what this says, so if you notice the backward and forward errors are all the same here. Okay, they're all guaranteed to the working precision, but if my condition number is 10 to the 4 or less, that means I can use half precision safely for the factorization with no consequences. Okay, I don't notice it at all. All right, as long as my condition number meets that bound. Right, so I don't lose any accuracy. Okay, and so here are just some plots. So this is a random SVD matrix in MATLAB. All right, so here's the infinity norm condition number, 10 to the 4. Now I'm using standard LU-based factorization iterative refinement with single, double, quad. Okay, and so here I am plotting the forward error, norm-wise backward error, and component-wise backward error versus refinement step. Over here, these are the quantities in the bound. Okay, and so phi is equal to a basically pink plus the maximum or minimum of blue or teal and orange. Okay, so as long as this this phi is less than 1, I expect to converge. Okay, so I have a slightly more ill-conditioned problem now. All right, condition number of A is up to around 10 to the 7, and you can see that my phi is closer to 1, so my convergence rate is slower. Okay, and then I go up to a more ill-conditioned problem now, 10 to the 10. Phi is 1. I don't converge at all, right? Using standard LU-based iterative refinement. Okay, and that makes sense because here my working precision, right, my factorization precision is single, so I expect my condition number has to be 1 over this U sub f, right? So after about 10 to the 8, I don't expect it to work anymore, and indeed it doesn't. Okay, so what can I do at this point, right? So I can go back and redo the factorization in higher precision and try this again. And if I insist on using LU factorization as my solver, that's the only thing I can do. Okay, an alternative is going to be to change the solver. Okay, so this is the only thing I can do here. All right, and so this leads to what I'll call GMRes-based iterative refinement. All right, so this is based on an observation made by Siegfried Rump and others that if my LU are these LU hat U hat are the computed LU factors of A and some precision U sub F, all right, then if I look at the condition number of the left preconditioned system using these LU factors as preconditioners, it's reduced by about a factor of U sub F times condition number of A. All right, this is true even if A is much more ill-conditioned, all right, than the factorization precision, right? So that means my my LU factors can be almost total garbage, and they still somehow make reasonable preconditioners. Okay, in terms of reducing the condition number, let me qualify. Okay, and so this is the idea behind GMRes-based iterative refinement. So it's the exact same, I'm just changing the solver. So now instead of using the LU factors just to solve, LUX equals B, right now I'm going to use the LU factors as preconditioners for GMRes. Okay. All right, so the iterative refinement scheme looks exactly the same. I'll still use LU factorization for the initial approximate solution, but I'm going to keep these guys around now and use them as left preconditioners. Okay. All right, and you can prove that here's this is, now it's clear why I introduced this effective solve precision, because if you do it this way, now my effective solve precision is the working precision rather than the factorization precision with some constraints. Okay, so here's the same plot I had before where I'm using standard LU-based iterative refinement in single double quad. This 2L condition doesn't work. Now, if I change the solver, right, still using single double quad, okay, now it works. All right. All right, and so just a quick table comparing the LU-based iterative refinement to the GMRes-based iterative refinement. Basically, so in the same precisions, half single double, the benefit is that GMRes-based iterative refinement can handle more ill-conditioned systems. Okay, and so if you're wondering where this 10 to the 12 comes from, that's because this is what the constraint actually looks like. Okay, so the constraint on my condition number has to be less than 1 over the square root of the working precision times 1 over the factorization precision. Okay, so this is pretty amazing, right? I can still guarantee double precision accuracy using half precision for the factorization if my matrix is ill-conditioned up to 10 to the 12. Okay, so to me that's pretty amazing. All right. And so before I get into the caveats on that, let me just show you some performance results. So these are similar to what I showed at the very beginning. Okay, and so here the orange is double, okay, purple is single, blue is half, and then the teal is half plus tensor cores. So this is using the GMRes-based iterative refinement approach, right? So here it's actually just using 2 precisions. It's using U for the residual computation. And the numbers above here, okay, this is just double precision, and then this purple, blue, and teal are using GMRes-based iterative refinement, and the numbers above are the number of GMRes iterations per refinement step. Okay. Okay, so if I have a diagonally dominant matrix, right, that's all well and good. Okay, here I have another nice matrix, right? So this is has positive eigenvalues with clustered singular values. Notice something here is that for some reason, okay, GMRes is, I need fewer GMRes iterations using the tensor cores than not using the tensor cores. Okay, and that's actually because they're doing higher precision accumulation, right? So they're doing this fuse, multiply, add. Okay, and we can see if it depends on the problem type, right? If I have a less nice problem, I start to require so many GMRes iterations using half precision that I go down to now I'm performing worse than just doing this in double. Okay, so the GMRes convergence rate, although not shown in the theoretical results, does actually play into how effective this will actually be on practical problems. Okay, so if I require many GMRes iterations, this is no good anymore. Okay, and maybe I will skip this in the interest of time. There's results on real problems too, not just these synthetic problems. You can look at this 2018 paper. Okay, and so this GMRes-based iterative refinement is implemented. People are using this. This is kind of what forms the basis for the HPLAI benchmark. All right, this is implemented in Magma and also in NVIDIA's cuSolver library, and people are also using it in applications. Okay, so now I'll get into the caveats, right? So the first is, I have to pick this convergence tolerance for GMRes, and there's obviously a trade-off there, okay, between, how many iterations I do per refinement step. Okay, and so again, I haven't said anything about overflow, underflow. I'm just assuming that doesn't happen. Of course, it can happen, right? And you can use sophisticated scaling techniques, which do in my experience, help in practice. Okay, and then the big one, which I alluded to, is what is the convergence rate of GMRes, right? Okay, so if, if A is very ill-conditioned and the LU factors are computed in a very low precision, theoretically it will, get, taken up to n steps, it will converge, right? But if it takes n steps, then this is no good, right? I would be better off, just redoing the factorization in a higher precision. Okay, right? And so the condition number was not necessarily indicative of this, right? I can have, I can construct a problem for which the condition number is 1 and GMRes won't converge until the very last step. Okay, and so there are potential. So this is makes it hard to predict, especially for non-normal problems in the non-self-adjoint case. All right, so there are a number of potential remedies, right? So I could throw another preconditioner in there. Okay, why not? I could use Krylov subspace recycling. And one of my PhD students has worked on adding this, and it does actually help. Right, the idea is that I'm doing a number of refinement steps. I'm solving the same linear system with the same matrix each time, right? So I can reuse information between refinement steps to actually speed up subsequent ones. Okay, there is also our theoretical analysis in this original work assumes that you, within each GMRes iteration, you are applying the preconditioned system to a vector accurately, right? So you have to, in theory, use double the working precision. Okay, this is not really true in practice, and it was observed that that's not true in practice. It's also not desirable in practice. And so there's a recent work that now changes this from 3 precision GMRes IR to 5 precision GMRes IR. So now you can also give bounds that don't make this assumption. So I have a working precision used within GMRes and some precision that's used for applying the preconditioner.
Does it make a difference if this is a householder GMRes or MGS or CGS2?
I can't say anything about CGS2, but for MGS and householder, yes. Ones that are known to be backward stable, so yes. I'm just assuming that it'll converge within n iterations at most, yeah. Okay, all right, and so for another question is why GMRes at all? Okay, and this was used, this is for theoretical purposes because we know it's backward stable, right? Saying things about CG and short-term recurrence methods is harder. You can maybe still say something. There are these backward-like stability results. In practice, really, you could use any solver you want. Okay. Okay, and so with the remaining time, I'll talk briefly about a couple extensions to this work. All right, and so we've already heard, in data science, a lot of times we're solving least squares problems. Least squares come up all over the place. Okay, all right, so I want to solve this least squares problem. All right, I can solve that using a QR factorization. Okay, and as in the linear system case, if my matrix is particularly ill-conditioned, I could do iterative refinement in order to improve the accuracy and stability, right, of this least squares solve. All right, and if I have an inconsistent linear system, which is usually going to be the case, you have to simultaneously refine the solution and the residual. Okay, and Bjork came up with a very nice way of doing this back in the 60s. He showed that I can write the least squares problem as a linear system with this augmented matrix. Okay, so I'm solving for the residual and the solution. And then I can just do refinement on this linear system, this augmented linear system. Right, so I'll compute the residuals, I'll solve for the corrections, and I'll update the solution. Right, and so in this way, I'm simultaneously refining both the residual and the solution. Okay. All right, so I can just write this in the exact same form. And so a nice thing is we can just say kind of automatically that the results for 3 precision iterative refinement for linear systems also apply to least squares problems. Okay, so one particular issue which I won't go into is so in the case of if I want to use GMRes-based iterative refinement for this, now I have to think about what my preconditioner is going to be. Okay, so I obviously don't want to compute the LU factors of this augmented system. I already have the QR factors, so I want to cleverly construct a preconditioner that will provably work well in GMRes consisting of the QR factors. Okay, and there are ways to do that. All right, and some other extensions. So there's recently with my PhD student, we came up with a multi-stage mixed precision iterative refinement. Right? And so the motivation here is that I gave this maximum infinity norm condition number for which these things work. That's often too tight a constraint in practice, right? So you'll see that even if the condition number exceeds that, these a given method and a given precisions might still work. Okay, and so therefore it's kind of non-obvious which combination of precisions, which solver I need to use, right? And so obviously doing a standard LU solve is cheaper than doing a GMRes solve, right? Since I'm doing an LU solve within each iteration of GMRes to apply the preconditioner. And so this is kind of a way where I, given 3 precisions, I start off with the cheapest thing, the standard iterative refinement. And then if I detect non-convergence, then you can detect non-convergence using some adapted stopping criteria that Demel and others have developed for normal iterative refinement. Okay, so the idea is instead of necessarily increasing the precision, now I can change the solver first before I result to increasing the precision. Okay, existing work is almost all assuming that you're using a Gaussian elimination with partial pivoting to compute these LU factors. In practice, you might want to use static pivoting, right? You might want to use a block low rank LU, right? And there's work on that in this recent paper of Amistoy and others. You also might want to use some inexact preconditioner, some sparse approximate inverse. And with my PhD student Noman Khan, we've showed that under what constraints, constraints I can use a sparse approximate inverse preconditioner within this GMRes-based iterative refinement and still guarantee that I will converge. Okay, and another thing, I'm working on this with my current postdoc, Eva Daujitsketa. We're using low precision in randomized preconditioners. Okay, so a lot of people are using, getting into randomized preconditioners. In particular here, we're proving that we prove that in many cases you can use basically much lower than double precision in constructing, for example, a Nystrom approximation, and then get away with using that as a preconditioner for conjugate gradient. Okay, all right, so to sum up, we know, already current machines support a range of hardware precisions. This is only going to expand in the future, okay, in the near future anyway. Okay, and we're already seeing new non-EEE compliant floating point formats. Right, so one example is this bfloat 16. Another example in this new NVIDIA H100 is the FP8 format, which is kind of dynamic. Okay, people are also getting, maybe positol. Maybe everyone will be using posits. I don't know, but there's a number. We can do, finite precision in a number of different ways, and I think it's kind of a wide open landscape as to which way will win out for which applications. Right, so a lot of machine learning people are going back to fixed point arithmetic, etc. So by using fewer and fewer bits, it's clear that there's a performance advantage. Right, I'm moving fewer bits, I'm computing fewer bits, I'm storing fewer bits. Right, so my arithmetic will be faster and more energy efficient. But whether I can get away with that is going to very heavily depend on my particular problem, okay, my particular algorithm, my data, right, and what answer I actually want, okay, what I as the user demand. And so as numerical analysts, I think it's our job and also our opportunity to determine when and where we can safely exploit lower precision hardware to both improve performance while still giving a satisfactory answer. Okay, thank you for your time.
There's a question in the chat.
No, someone has just pointed out that the Fujitsu ARM also has half precision. Yes, indeed.
What is the status of standard language and compiler support for all of these? Like, I can't compile my C code on my MacBook to get FP8.
Yeah.
What's language?
I mean, I think. Okay, so you need to have one of these special GPUs. I think that from the user perspective, these will hopefully be implemented in like kublas and things like that. I think already if you're using kublas that they're using these that it compiles down to calling these tensor core instructions.
Question. So I know in math, if you do your experiments in MATLAB, you have to simulate with more precision. You know, right? So it's in Julia, is it possible that can you do it more easily?
Probably, yeah. I haven't tried, but I would suspect yes. I would suspect it's easier in Julia. I haven't tried though.
The other question I have, and I'm asking is about using geometry.
Yeah.
And so I guess the reason is are you orthogonalizing the number vectors as you go? Is that necessary to guarantee these accuracies?
So I'm using the modified Gram-Schmidt version, no reorthogonalization. So I know from this page Rozlužník and Starkos result that it'll be backward stable. And so we've kind of adapted their proof to the preconditioned case. Of course, if it works for MGS, I would assume it works for Householder. But yeah, no reorthogonalization.
Yeah.
Mhm. Yeah. You mean if it works on a non-symmetric matrix? I don't know. I think you know better than me. I don't know. Okay, so I have talked to people like Daniel Krester, who knows a guy who has some application where they're using CG for a very slightly indefinite problem, for example, and it works. And this works for them. I don't know why. We've been kind of chatting about, can we prove when and why that works? So I don't know. If you don't have positive definiteness or symmetry, I don't think that there exist any theoretical results saying anything. Right. Right, so where I'm changing the preconditioner. Yeah, maybe. Yeah. I'll think about that. Thanks.
Yeah, so if you think about our entire background in a symmetrical forms, so is there any rule of thumb or any intuition which really have to do it in a decision there is whatever part of the case?
I think anything that is, any computation that has questionable stability or anywhere there's a ill conditioning, that's where you should use higher precision. Of course, if you have, I think you can get away, you can get away with low precision when you have some kind of self-correction mechanism. Okay, like is in the case with iterative refinement. So, and I think there's not just iterative refinement, but any kind of stationary iterative method, Newton's method, things like that, all kind of fall into this category.
Okay, by the way, so I need some of the videos there, but when you're doing the refinement, is it every month or there, or you're actually using the U precision, or maybe some of them could be you have, or some of the others will actually have to do this too?
So so in traditional iterative refinement, the U squared is just for the residual computation, and that gets rid of the condition number in the forward error term. So if you don't really care about that, you can just use
So for example, so when you're replacing the second line there, that would just then what happens to the GMRS section?
Oh, what happens within GMRes? Right. Okay. Yeah, so like I said, so the original analysis and the stuff that was in the tables I gave assumes that you're using double the working precision in applying the preconditioned matrix to a vector. Okay, that is overly pessimistic in practice. A lot of people observed, and there's this new paper of Amestoy and others that's called 5 precision GMRes based iterative refinement, if you just Google that. And so they have 2 other precisions. So they have the working precision within GMRes and the precision with which the preconditioned matrix is applied to a vector. Right, so you can set both those to U and plug in and get error bounds. Of course, there, the resulting condition number constraint is smaller, is tighter. So you can only guarantee that it will work for more well-conditioned systems than the case where you're using extra precision there. But in practice, it works a lot of the time, even for more ill-conditioned. Yes.
I'd like to make a comment or two. For us in electronic structure theory, what is really would be useful is something, maybe an 80-bit words or something, because the 64-bit limits with these bigger calculations are now visible.
Mm-hmm.
And what, on the other hand, is a little bit of a too much,
I see.
too slow. So I don't know. Unfortunately, takes a significant investment in developing CPUs,
Mm-hmm.
and the people who do that don't really care about us. They work for the gaming industry and AI and other things, which so they. But I mean, in scientific computation, that would be important. The other comment is that, no, to us at least, speed up by a factor of 2 or so, well, it's essentially noise.
Mm-hmm.
It's not too significant. I mean, buy a bigger computer or newer computer and get my factor of 2. Now the speed up begins at an order of magnitude.
Yeah, but yeah, sure. But I think right, if you look at the results comparing this HPL AI to the HPL benchmark, it is like a factor of 10. It's an order of magnitude, which I think it's not.
Sometimes it's actually limited by how much you have. So if you have a machine that can give you only 8 bits or 16 bits, then you have to limit that.
And I also think that this is a totally excellent point. There are a number of areas in computational science where people have been saying for a long time, we need more precision. Okay, and so it seems that people are going the opposite way. So I think that that's,
But actually, our data supports for higher precision for floating points. For integers, we have quick integers.
yeah, for floating point numbers. I mean, people implement this in software, and it's slow.